Okay, is the screen visible to you? Okay, perfect. So we can start. So before second sessional exam, we discussed a lot of concepts related to the DES, that is data encryption standard. Right, so the DES encryption mechanism and decryption mechanism and many important things we discussed. So a brief about that, and then we begin with the remaining part of the DES topic. So the DES encryption can be seen as this sequence. What is the plain text size? Can anyone tell? In DES, what is the plain text? That is 64 bits. Okay, 64 bits block, right? So that you can see that your plain text is divided into the blocks of 64 bit. And then the first step, that is IP. What is IP stands for? Initial permutation, correct. And then it follows 16 rounds, round 1, round 2, round 15, round 16. In each round, it takes K1, K2, K15, K16, right? What is the size of this K? K1, K2, K3? 48 bit. And this 48 bit key is generated from which size of key? 56 bits, correct, right. So we have this 48 bit key and round function is applied, and this 64 bit key is after round 16 is it goes through final permutation and it generates ciphertext of 64 bits. Okay, and in the similarly on the decryption side, we have ciphertext as an input, which is again of 64 bit. Then again we perform initial permutation, right? And then we have 16 rounds, but in each round we have key values which are in reverse: 16 K16, K15, and then in 16th round we have K1, and then we follow the final permutation, and that should generate plain text of 64 bit. Okay, so initial permutation and final permutation are inverses of each other. These are two tables, right? So encryption and decryption rounds are little different structure wise, as we had seen in the earlier lecture also, for 2 rounds, right? And that was also discussed, and its proof was also discussed in the last lecture. So this key generation topic was also discussed. Cipher key with parity bit, right? So in this DES encryption here, you get 48 bit key that is generated from 56 bit key. But in case if you have cipher key with parity bits or cipher key with 64 bit, then you can apply this parity dropout and it should generate cipher key with 56 bits. So for that, this 56 bit key is then again divided into two halves, 28 bits block of each. That is then followed, it goes through the process of shift left, and then compression D-box converts this 56 bit key into 48 bit, right? So parity dropout drops 8 bits and generates 56 bit. This 56 bit goes through shift left of two halves, and then again compression D-box converts it into 48 bit key, which goes as an input to the round 1. So this round 1 to 9 and 16 follows 1 bit shift to the left, and others follows 2 bits left shift, and it goes through all 16 rounds, and finally it that goes to the uh, each round input, right? Now we discuss some properties related to the DES. One of that is avalanche effect. Avalanche, anybody understand avalanche, where it happens? Recently there was a news related to the avalanche kind of scenario. Anybody remembers? On the snow mountain, right? On the mountain where there is a lot of snow, which happened recently in Ladakh and Arunachal area, right? So a lot of snow was there, right? So when avalanche takes place, it's a kind of storm of snow, right? So it happens on a mountain, right? So huge amount of snow comes with force. So that is the avalanche, right? So that type of effect takes place in this DES. Let us see what is the meaning of this avalanche effect. So it means a small change in the plain text or key, right? Plain text or key should create a significant change in the ciphertext. So even if you make a small change in the plain text, right, there will be a huge impact on the ciphertext. So the rate of change is huge. That is the meaning, right? So DES has been proved to be strong with regard to this property. So in DES, we observe that this avalanche effect takes place. And one example related to that, let us see. Suppose our plain text is this 64-bit 0000, and you have 16 such zeros, and this is in hex. So 16 into 4, 64. So this first plain text is all zeros of size 64-bit. And when you convert this plain text with this key, okay, this key is 2223 4512 987A BB23 in hex. Okay, so this 64-bit key, ultimately, as per the key generation, this 64-bit key after parity dropout becomes 56-bit key, and this 56-bit key goes as an input to the 56-bit key generator, which generates 16 48-bit keys. And after final permutation, it produces this ciphertext. Ciphertext 4789 FD47 A5 F1 in hex, right? So 64-bit hex ciphertext, 64-bit ciphertext is generated. Now, if we make change in a plain text, so this second example, which you see, that in this our input is 0000, 0000, 0000, and last 0001. So the difference between first plain text and the second plain text is of only 1 bit. Okay, only 1 bit difference. Now, if you look at the key is same as it is used in this example. Okay, the key is same. So if we compare this ciphertext, so there is only 1 bit change in the plain text, but the ciphertext, if we see, there is a huge change, right? So these hex values are totally different, and you don't find the similarity here over here, right? So this is called as avalanche effect. Okay, let me show you in this slide also. So the same example, you can see the keys are same and the output ciphertexts are different. So it is observed that these two plain text blocks differ only in the rightmost bit. The ciphertext blocks differ in 29 bit. So 1 bit change has an impact on 29 bits in the ciphertext. So if you take percentage wise, then only 1.5% change in the plain text that creates approximately 45% change in the ciphertext. Okay, 29 bits of 64, that is 45% of change. Right? So the number of differences for this plain text as per the round, right, 1 round up to 16 round, is this 1, 6, 20, 29, 30. So the number of bit differences that you can see are this per round. So this shows that there is a significant bit differences, right? 45% change. This is called as okay, I got disconnected and reconnected. Uh, are you able to see? Please confirm. Are you able to see the slide? Can you hear me? Okay, all okay, right? Okay, okay. So completeness effect, second effect is completeness effect. It means that each bit of the ciphertext needs to depend on many bits on plain text. Now this is a mapping of many plain text bits actually becomes dependent. It creates a dependency on 1 bit of ciphertext, right? And this has, how do we say this? Because we have D box or P box, permutation box or D box, and S boxes. There are 8 S boxes, right? And this show that there is a strong completeness effect, right? So let us see this in slide also. Completeness effect means each bit of the ciphertext needs to depend on many bits on the plain text. And if we see S boxes, so the design provides confusion and diffusion of bits from each round to the next. Okay, now this generates two terms, confusion and diffusion. Okay, so let us understand this terminology. What is diffusion first? So diffusion means it implies that each symbol in the ciphertext is dependent on some or all symbols in plain text. So there is a dependency. Okay, so symbol means character per bit. This this term is used in the context of information theory. And in communication, whenever you are transmitting data at the physical layer, when it is transmitted, it is actually a binary transmission. 0 and 1s are transmitted. But 0 and 1s are transmitted, it is measured in the form of symbol, that is character per bit. Okay. So there is a separate subject of information theory. Okay, information theory. and you can measure entropy. There are some topics which might be of your interest, um, maybe later or if time permits, or you can refer entropy of a like entropy you have studied in the context of science. Here also the entropy terminology comes. So this is for your additional information. So diffusion implies that each symbol in the ciphertext is dependent on some or all symbols in the plain text. Okay. So in other words, we can say if a single bit in the plain text is changed, several or all symbol in the ciphertext will also change, right? And diffusion actually hides the relationship between ciphertext and the plain text. Right. So if there is a diffusion, the crypt analysis becomes difficult because with the help of only ciphertext, it becomes difficult to establish a relationship because of the presence of the diffusion. And as you can see in this slide, that S box actually creates this kind of diffusion. It also creates the confusion that we see next. Similarly, P boxes also create diffusion effect. Okay. So what is confusion then? Right. So diffusion means each symbol in the ciphertext is dependent on some or all symbols in the plain text. And the confusion means the idea of the confusion is to hide the relationship between ciphertext and the key. So there are three things: plain text, key, and ciphertext. So the relationship between plain text and ciphertext is hidden by the diffusion, and the relationship between the key and the ciphertext is high is kept as hidden by confusion, right? So this will frustrate the adversary who tries to use the ciphertext to find the key. Okay, so these terminologies are used. So if a single bit in the key is changed, now we use the term key. Okay, remember key. If a single bit in the key is changed, most or all bits in the ciphertext will also be changed. So we have three variables: plain text, ciphertext, and key. So if we change plain text, one bit in plain text, it creates a significant change in the ciphertext. If we create one bit change in the key, then also it creates significant difference in the ciphertext. So these two properties are included into this DES with the help of this S box and P box, right? So S box provides confusion and diffusion both. And what is there in the S box design? You remember 6x4 S box, and you have 8 such S boxes. Symbol is not a character, it is character per bit. It is the context, as I already mentioned to you, in the context of information theory. Or if you have your electronics and communication friend, he will discuss with you the basic concepts of communication. It is actually, so this communication and this security, network security, merges in the information security branch. So information security is, as so in a brief, I will give you idea. See, when we are saying, there are two terms. One is information security, and second is network security. So information is your message, and we are talking about that. So the message is encrypted, but then it has to be transmitted. That is done on the network. In case of wireless transmission or wired transmission, mostly in the context of wireless transmission, when you are transmitting the information, that information is transmitted in the form of a symbol. But what is a symbol? So symbol is character per bit, that is given here. See, here symbol means character per bit. Okay, so literally you don't have to convert it, it has a meaning, right? I just recollect Shannon just uh, search. He was a great scientist who actually gave very important principles on information theory and communication. Okay, Shannon's principle. Okay, these are he provided actually some theorems related to the information theory, entropy, Shannon's theorem are also signals and system. Those you, if you want to discuss this thing with your EC friends, uh, ask them if they have studied the signals and system. There is a subject called signals and system in electronics and communication branch, or electronics or digital communication. So if they have studied signals and system or digital communication, they will provide you more information about this. It is very fundamental concept, very fundamental. Okay, if you want to measure the bandwidth or error and at the physical layer, how it transmits and what kind of errors are generated, all these things can be done at bit level, right? So we have to uh, see whether one bit transmission is successful or not. So these are very in-depth discussions which are out of scope of this subject, but you can discuss further with your friends for further information. So we restrict ourselves to the discussions of encryption and decryption, right? And the ideas of DES in this particular uh, topic. So the number of rounds, DES uses 16 rounds of Fistel cipher, and the ciphertext is thoroughly a random function of plaintext and ciphertext. Okay. Uh, Now, at this point, I would like to discuss one more example. So this example was discussed in the last lecture. This was the last example where I demonstrated you how the plain text is converted into ciphertext with this key and what is the output of each round. And that you can see that first, after initial permutation, two parts are divided, L0, R0, and this L0, R0, we get L1, R1, L1 is R0, and R1 is after applying that round function, right? So, and the same thing is applied over here. Now, we see second example. So, in this example, you see that you have a ciphertext, right? So, Bob at the destination can decipher the ciphertext received from Alice using the same key. So in the example we use this ciphertext. This ciphertext is generated and this key is used. So in reverse, we use the same ciphertext as an input, and we use the same key, and we after generating the initial permutation, we again follow this L0 R0, divide it into two parts, and then L1 becomes R0 and R1 becomes, again following that formula which I discussed in the previous class, and the round key is used, and after 16 rounds which it follows, it generates final permutation, and that becomes your plain text. So the you recover the plain text from the ciphertext. So in the beginning, I explained you the uh, decipher process, and this is the example of that decipher process. And we discussed the properties, and now we discuss some weaknesses. But before that, there is an important property. When can you say that S box is non-linear? Okay, S box is non-linear. Okay, so this is very interesting thing. Uh, when we can say S box, what is the S stands for in S box? Yes, anybody? How many S boxes we have in DES? 8. Okay. Okay. And what is the input? Very good. Very good, yes. How many bits of input in each S box? 6. And how many bits of output? 4. So total how many bits goes to 8 S box? 8 S boxes? 48. And how many bits it generates in the output? 32. 32. Okay. So that is one half of that ciphertext. The other half also generates 32 bit and both goes through each rounds. Finally, it produces 64 bit. Okay. So in this each round, we use S boxes. So is this linear or non-linear? So it is a non-linear, but how we can say that? So for that, we have S, X, X or Y, this relationship. If S, X, X or Y equal to S, X, X or SY for every XY, if this is true, then we can say linear. But if we find some XY pair for which if this is not true, then we can say that it is non-linear, right? So we check whether S boxes of DES are linear or not. So if we can find at least one pair XY such that S XOR Y is not equal to SX XOR SY, then S is non-linear. Okay, so we have to prove this. So to prove this, we take X and Y values of this. Okay, in the slides, we have S1 table. So let me go back to one of the S1 table. See S box table, S box 1. Okay, this table we will use. So X value is 0, 1, 0, 1, 1, 0. Okay, and Y value is 1, 1, 0, 0, 1, 0. Okay, so what is the value of S1X? S1X means this X value whose this X value is the input, 6 bits input. So what is the output? Okay, so how we can find X, S1X? Can anyone tell how we can find? Which we have to find row column, right? Do you remember row column? So in X, which row and which column we have to observe? First and last bit, that is 0, 0. Okay, so 0, 0 indicates row number 0 and then column number 1, 0, 1, 1. 1, 0, 1, 1 is equivalent to which column number? 0, 0 and 1, 0, 1, 1 in 8, 4, 2, 1. It is 8 plus 2 plus 1, right? So 11, right? So 0 and 11, row number 0 and row number 11, that we have to observe in S box 1. So this is row number 0 and column number 11. And what is the output corresponding to that? 12. In decimal, it is 12, right? Okay, so 0 and 11, so you can see it is 12. And that we are taking over here. So S1X is equals to 12 in decimal, whose binary equivalent is 841100. Okay. Now we take Y. Okay. So Y is 1 1 1 1 1 0 0 1 0. So S1Y we want to find. So which row number we have to observe? Row number 10, first bit and last bit. 10 indicates 2 and column number is 1001. That means 8 plus 1, 9. So row number 2, Janil, it is 19 or 29? Okay. So let us see this row number 2 and column number 9 and see what is the value 12. Can you see this? 12, right? So we are taking that. So S1Y is also 12. So its equivalent binary is 1100, right? Now what we do, this SX and SY we have found. Now X XOR Y. So this is X and Y. So if we perform X XOR Y, then 0 XOR 0, that is 0. 1 XOR 1, that is 0. 1 XOR 0, that is 1. 0 XOR 0, that is 0. 1 XOR 1, that is 0. And 0 XOR 1, that is 1. So we have found 1 0 0 1 0 0 as X XOR Y. Now this becomes our input and we want to find S1 X XOR Y. So which row and column we have to observe? First bit and last bit, that indicates 1 0. 1 0 is equivalent to 2. Then middle 4 bits 0 0 1 0, that is also equivalent to 2. So row number 2, column number 2. Let us see what is the value. Row number 0, row number 2, column number 2, and its value is 14, right? Okay. So 14 in decimal is equivalent to 1110, right? 8 4 2. 8 plus 4, 12 plus 2, 14, right? So 14D. So 1110 binary 2. Okay. So now we should check whether S1 X XOR Y is equal to S1 X XOR S1 Y. You try to find out this. Please do this. 1100 XOR 1100. So what is the result of 1100 XOR 1100? 0000, and it is clearly not equivalent to 1110, right? So you can see S1X XOR S1Y is 1100 XOR 1100. So that is 0000 binary 2, and it is equal to 0 in decimal. So we can say that S1 X XOR Y is not equivalent to S1 X XOR X1Y, and for these X and Y values. So in general, S1 to S8 of DES are non-linear. Okay, is that clear to all of you? S1 to S8 are non-linear. Is that understood? So we discussed it in the context of S1 table, but the same way you can find X and Y value for each S boxes, and then you can say that it is a non-linear. No, non-linear means this. I told you that linearity, this is the principle of linearity. X XOR Y is equals to Sx plus XOR Sy. This is the meaning of non-linearity. If this equation S XOR Y is not equal to SX XOR SY, then we can say it is non-linear. Non-linear. We are not saying not order. Non-linear. Okay. So what are the weaknesses in the cipher key? Okay. What are the weaknesses in the cipher key? So we are using this DES, but whether it has any limitations. So these limitations are basically found with the analysis of the DES, and they are classified into these weaknesses of the DES. So what are the uh, possible, how many keys are possible? 2 raised to 56 possible key, because we have key length of 56 bit. So it means if this condition, this is the definition of non-linearity. Okay. Okay. So weakness is 4 out of 2 raised to 56. Now we have key length of 56 bit. So we have 2 raised to 56 possible keys. Okay. And 4 out of 2 raised to 56 bits are called as weak keys. Why weak keys? Because key is a weak key is one after parity drop operation. Okay. So we have 64-bit keys cipher key that is generating 56-bit key. So we are dropping 8 bits, which consist of either all zeros, all ones, or half zeros and half ones. So you can see that original 64-bit key is 0101, 0101, 0101, 0101. And so this is one possible key. Okay. This is of 64-bit. So if we apply parity bit, you can see in the beginning, here we have seen that 64-bit key parity dropout generates 56 bits. So it drops 8 bits. Okay. And there is a table. There is a table of parity bit dropout. Let me go back to that slide. So this is parity bit table. Okay. Just recollect it. Just recollect it that only these 56 bits are supposed to be taken. 1, 2, 3, 4, 5, 6, 7. 7 rows and 8 columns. So 8 bits are dropped. Which 8 bits are dropped? Bits in the multiple of 8. 8, 16, 24, 32. These bits are not present. Okay. So if this parity bit dropout is applied, then this all ones will go. So 56 bit is what is remaining is 0, 0, 0, 0. So these are all zeros. Okay. Similarly, if you see the last key, F E F E F E F E F E F E F E F E, out of these 8 bits are dropped. So we have all E. Okay, all E. These bits are dropped. So finally, 56-bit key becomes all F. F means 1. Okay, F means 1. So all zeros, all 1, or these two keys, key number 2 and key number 3. 1F, 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 0E, 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 0E. And this one is reverse. E0, 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 F1, 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 F1. So in this, after parity dropout, it generates half zeros and half ones and half zeros. So these four keys are actually weak keys, right? What is the disadvantage of weak key? Let us see it in an example. So this is the example for discussion. So if we encrypt a block two times, so after two encryption with the same key, the original plain text block is created. Okay, so just recollect that we had seen example in the our plain text is 1 2 3 4, and this with this key, this is weak key 0 1 0 1 0 1 0 1. We get this cipher text. Now again we apply ciphertext with this key, we get a plain text. So after two encryption algorithm, we get the same, right? So double encryption and decryption in a weak key. So you can see that 64-bit plain text goes through DES cipher with a weak key. Again, it goes through a DES cipher with the weak key, generates the same plain text. Similarly, in the cipher text, at the bottom, ciphertext goes through DES inverse cipher with weak key, goes through DES inverse cipher with weak key, two rounds, two times DES cipher, and then it generates same ciphertext, right? So this is about weak key. So the disadvantage is that plain text after two times DES generates the same plain text. So we have actually nullified the effect of the encryption with weak key. Second type of weak key is called as semi-weak keys. So in weak key we have all zeros, all ones, half zeros, half ones. Okay, four such keys. In semi-weak key, it creates only two different round keys, and each of them is repeated 8 times. So we require 16 keys, K1 to K16. So it creates only, so one key is appearing after every second round. So in 8 round, we use 16 keys, right? So in addition, the round keys are created from each pair. They are same with the different order, right? So it is changing the order only, right? For example, 01 FE, and the second key is FE01. 01 FE, FE01, right? So this is just change in the order. So there are 12 such semi keys are there. So with the, if we use semi weak key K1 and K2, and if we apply it on DES, two rounds of DES, it generates the same plain text. Okay, so let us see it here in the slide. These are the semi weak keys: 1 2 3 4 5 6, 6 into 2, 12. So if you see this first key 01 FE, 01 FE, 01 FE, 01 FE, and this second key is just actually change in the order of this key FE01, FE01. This second key 1F E0, 1F E0, 1F 0E F1, 0E F1, 0E F1. So this first four are changed in the order E0 1F, E0 1F, E0 1F. 0E F1, F1 0E, F1 0E, right? So we have 6 such keys, and six keys on this side and 6 keys on this side, which is just a change in the order. So 12 such semi keys are present. So you can see that round 1 key, after round key 1, this one, then in the key 2, So you can see that 1, 2, 3, 4, 5, 6, 7. It appears again the same key, right? You can see. So it is actually not creating any good benefit into the encryption. So after 2 rounds, it generates the same plain text. Now, third is possible weak keys. Third type is possible weak keys. We have seen this weak key, semi-weak key, 4 weak keys, 12 semi-weak keys, and now possible weak keys. So in possible weak key, it creates only 4 distinct round keys. Okay, and there are 48 such keys. So 3 types of weak keys. All, see, there are 2 raised to 56 keys. Those who have observed this, they have observed that out of these keys, okay, you will understand, generated using changing order means if you create 2 raised to 56 permutations, out of this, these 4 keys are going to be this as I listed, and then 12 keys are going to be like this. It is permuted. Okay, if you these are basically 0 1s, permutations of 0 1s. Okay, so you will understand it in this next question. What is the probability of randomly selecting a weak, a semi-weak, or a possible weak key? Okay, what is the probability? Can you find out the probability? Can anyone find out? You know the values of weak key, total weak key, semi-weak key, and possible weak keys. Can anyone find out what is the probability? See, it is very simple. Once again, I'm going back to the point from where we started this weakness. See, there are 2 raised to 56 possible keys. How it is 2 raised to 56 possible keys? Can anyone tell me? I explained it at that time. The key length is of 56 bit. So how many unique keys are possible? So the number of unique keys are 2 raised to 56. Why? Because the key is having 0 1s, right? Key is using only 0 1. It is a binary, right? So 2 raised to 56. So out of that, 4 keys are listed over here. 56-bit key, these are listed over here. These are going to be there. Okay. So each one is a new key, but it is a key which is after permutation. But there are 4 in number, fixed. Then there are semi-weak keys. So semi-weak keys are also fixed, and they are 12. It is observed that there are 12. And there are 48 possible weak keys. So what is the probability of randomly selecting a weak, a semi-weak, or a possible weak key? It means that if you are supposed applying DES cipher and you are using this key generation, and what is the probability that K1 to K16 may have a weak key, a possible weak key, or a semi-weak key? What is the probability? Okay. Okay. So let us see the solution. So the number of keys equal to 2 raised to 56. number of weak keys equal to 4, number of semi-weak key equal to 12. So number of possible weak keys equals to 48. So total number of keys, weak keys are 4 plus 12 plus 48. So 64 keys. Okay. So probability is equals to 64 divided by 2 raised to 56. So that is equivalent to 2 raised to minus 50. This is equivalent to 8 into 8 into 10 raised to minus 16. Okay. And this is very low probability. So it is almost impossible that if you apply DES, there is a possibility that it will use weak key. So the chances that a weak key will appear, they are very, very less, or we can say it is almost impossible. Is that clear? So you may think that if we use 56-bit key, then it is, and there are 64 such keys, then it is possible that even if we apply DES, it will not perform the encryption properly. But how much is the probability? The probability is negligible, very less, very less. Okay, 10 raised to minus 16 probability. This is very less. So we can say it is almost impossible that you will use DES and it will use weak key. So there is a concept of key complement. Okay, let us understand this key complement. Key complement means this is the property that C is equals to DES PK. What is P? P is plain text, K is key. So if we apply DES on this plain text with key K, it generates ciphertext. So the complement of this is that if you take complement of plain text, if you take complement of key and you apply DES, then it generates complement of ciphertext. This is very interesting property. Okay. That means plain text complement you take, keys complement you take, and you apply the DES. So it is actually generating complement of ciphertext. Okay. And similarly on the inverse side, if you apply ciphertext and key over DES inverse, it generates P. So if you take complement of ciphertext, if you take complement of key and apply DES inverse, it generates complement of plain text. Okay. So this fact, now this is the property which if cryptanalyst knows, it will be easy for it will be useful information for cryptanalyst to decipher. So this fact can be used to do the cryptanalysis. For brute force, you can test only half of the keys and then complement the result to get the result for all 2 raised to 56 keys. So if we use this fact, then the total number of time we have to apply brute force reduces, the number of requirement reduces, because if you generate half of the time it generates complement. So security, okay, let me go back to this slide. So this is discussed. This example is discussed. Key complement is discussed just now. Let us test the claim about the complement keys. So we have used arbitrary key and find the corresponding ciphertext. So the original key and complement is this plain text and complement and ciphertext in its complement. So this is discussed. Okay. Now there is a concept in of meet in the middle attack. Now, this is to discuss this. Let us understand the security of DES. So, brute force requires 2 raised to 56 keys. As I discussed, that if we apply this complement fact, then we have to divide 2 raised to 56 by 2. Half of the keys we have to test. So, 2 raised to 56 divided by 2 is 2 raised to 55, right? So, if we apply key complement, then also it is 2 raised to 55. So even by half, it is not actually a reducing significant number, only one difference. So 2 raised to 55 is still large number, and it is brute force is very complicated. So brute force is very difficult. There is a concept of differential cryptanalysis, which we will discuss later. So there is a concept of linear cryptanalysis. Now this is relatively newer. So let us discuss this context. I discussed this part, meet in the middle attack. So here we see this 2 times DES. So this is another concept. The concept says that instead of using DES 1 time, you use DES 2 times over a plain text. So you can see this design. Plain text goes through DES with cipher key K1 56-bit. Then it uses another cipher key and it goes through whole of the DES again. Okay, this is not one round. This is whole DES again. So it generates some ciphertext. That ciphertext again goes through the DES and it generates the and ciphertext, right? So the key length required is 56-bit plus 56-bit, so 112-bit. So this results into 112 bit of encryption, and brute force is impossible. So we can say that 2DES is composition of DES, or 2 times DES into DES. Now this 2DES can be attacked by meet in the middle attack. Now what is meet in the middle attack? So if you see, observe this plain text, DES with K1 generates some X, and that X goes through the DES with K2 and it generates encryption, ciphertext. Now, if you see the ciphertext, it applies DES inverse with this K2 first and it generates X. Okay, then it applies DES inverse again with K1 key and it generates a plain text. So X is equals to DESP K1 and X is equals to DES inverse K2 of C. C is equals to DES X, DS of X with key K2 and DS inverse, right? So this two set and this two set, and if so we can say that DSP of if we apply plain text encryption with K1, it is equivalent to ciphertext decryption with K2. This is the important observation. Okay, and this is chosen plain text attack, and we assume that Eve has L pairs available. Suppose PICI pair is available, L such pair is available. So a table can be created, table 1 and table 2, with K0 to K2 raised to 56 minus 1. So P1, P2 and PL, and it generates DES, so it encrypts the first middle value, then it generates with K2 key ciphertext, L ciphertext, and it generates this table. So it will find with this equation that we need to search row I of table 1 and row J of the table 2 such that all values agree. And so row I of table 1 is same as row J of table 2. Okay. Okay, so I stop here for today and we will discuss the remaining of the DES in the next class.